In this video, I'm going to present Storm, a new web framework that ensures the absence of information leaks automatically and at compile time. Information leaks have been for almost a decade among the top 10 security risks published by the Open Web Application Security Project. We argue that this will continue to be the case unless we change the way we build web applications. Consider this code taken from the hot CRP site. The highlighted parts are security checks that control what a user can see or do, and they should conform to the complex security policies the site is subject to. As these checks are spread all over the code, they are easy to forget by mistake, causing potential information leaks. On the other hand, these checks are not only relevant for policy checking, but are also necessary for the business logic, as the application should react gracefully to a user not having access to some data. So in practice, it is common to spread security checks throughout a code, which makes it hard to guarantee they conform to the application's security policies. A promising approach to help with this issue is to let programmers specify their policies declaratively and separately from their application code, and then let an information flow control framework ensure that the code satisfies these policies. The key benefit is that programmers do not need to worry about getting their policy checking code right, but only worry about the policy specification, which is in practice much smaller. IFC frameworks typically come in two flavors, static and dynamic, both with different trade-offs. In this work, we focus on static techniques that eliminate information leaks at compile time once and for all, avoiding unexpected failures and overhead at runtime. On the flip side, dynamic techniques support richer policies which current static techniques cannot handle. Our solution is a new static IFC framework called Storm that, unlike previous static techniques, support automatic checking of rich policies. Storm is loosely based on the model view controller architecture, allowing programmers to specify their policies alongside the model definition and then automatically verify that the information flow in the controller conforms to these policies. In the rest of this video, I'm going to first give an overview of Storm by describing how to build a small example wishlist application. Then, I'm going to go over the key aspects that allow Storm to prevent information leaks automatically and at compile time, to finish with an evaluation of the framework. Imagine a wishlist application where users can post and share their wishes. Other users can visit someone else's profile, and by default, they should be able to see all the wishes unless they are marked as private. Informally, we want to enforce the following policy. Only the owner of a wish should have access to their private wishes. Let's see how we can specify this in a Storm. We start by defining the tables in the application, as we will do in other similar web frameworks. For simplicity, we're just going to consider two tables, user and wish. The user table contains two columns, a name and an email address. The wish table has a column identifying who is the owner of the wish and a column with its description. We will also define an access level column to mark wishes as either public or private. With everything in place, we can now formally define the policy described earlier. In a Storm, a policy is a predicate over a row and a viewer of type user. That is true if the viewer has access and false otherwise. In this case, the policy only public is true for wishes with access level equals public or if their owner equals viewer. After defining the policy, we can attach it to specific fields. In this case, we attach the policy only public to the description, meaning that the description can only be accessed by viewers satisfying the policy. Let's now see how we can write a show wishes controller that returns the list of wishes for an arbitrary user identified by UID. This controller first selects from the database all the wishes owned by UID. Then, it projects the descriptions out of the wishes, to finally respond with the list of descriptions to the session user who initiated the request. As you may have noticed, written like this, the controller may leak some information, as the session user may be requesting someone else's wishes. Storm detects this error at compile time by first inferring that the query will return all the wishes owned by UID, including the private ones. Then, using the policy in the description, it determines that the result of the projections depends on values that should only be viewable by UID. Finally, it complains that by calling respond, the results can be observed by the session user who may be different than UID. In this case, we can easily fix the code. We can do it by first getting the current session user, and then add some extra policy checking code to issue a different query depending on whether the session user is asking for their own wishes or someone else's wishes. We will see now how SORM scales up to more complex policies. For that, we're going to add social capabilities to the application by letting users have a list of followers and restrict public wishes so they are only shared with followers. Informally, we want to add the following restriction to the policy. Public wishes should only be viewable by followers. Let's see how to define this in SORM. We start by defining a follows table where each row indicates a follows relationship between a follower and a followee, with a status marking if the follow request is either pending, accepted, or rejected. Now, the key insight to specify the new policy is that the row in the follows table witnesses the follows relationship between two users. We can make this notion manifest in two steps. First, we declare the relationship as a binary predicate between user IDs. Second, we assert that for each row in the follows table, the relationship holds between the followee and the follower only if the status is accepted. With the definition in place, we can now update the policy on the description to require public wishes to be viewable only by those viewers that follow the owner. Let's put all of this into use by writing a notify followers controller that emails the wishes of some user UID to their followers. The controller first queries the list of wishes owned by UID and projects out their descriptions. The list of wishes is restricted to those marked as public, as only those are viewable by followers. Next, the list of followers can be accessed by querying the database for all the rows in the follows table with followee equals UID and status accepted. Finally, the controller uses the function sendMail to send a notification with a list of descriptions to all the followers. Note that to prove the absence of leaks in this code, the SORM needs to track both the users observing the data and whether they are authorized to see it. Let's dive in and see how SORM is able to do this automatically and at compile time. The notify followers controller can be divided into two sections. The top one, highlighted in green, reads sensitive data from the database. The bottom one, highlighted in blue, sends this data to a set of users. We say that in the top section, the data read from the database will only be viewable by a set of authorities, and that in the bottom, the data is sent to a set of observers. More concretely, a controller is composed by a sequence of statements. To track the information flow, the SORM assigns to each statement two sets auth and opt. Auth under-approximates the set of authorities of the data read in the statement, and opt over-approximates the set of observers the statement sends data to. When sequencing two statements S1 and S2, the SORM ensures the correct information flow by checking that the set of observers of S2 is authorized to see the data in S1, or in other words, that opt2 is a subset of auth1. Additionally, because the sequence of the two statements reads data both from S1 and S2, we assign to the composition the intersection of auth1 and auth2. Similarly, as the composition sends data both to observers in S1 and S2, we assign to it the union of ops1 and ops2. To do all of this automatically, SORM represents the auth and opt sets as predicates on users. For example, the predicate that is always true represents the set of all users, and the predicate that is always false represents the empty set. As additional examples, we could also have predicates to represent the set of followers of UID, or the singleton set that only contains the session user. This means that when we want to sequence two statements, we can prove the inclusion between the ops and auth sets by resolving whether an implication holds. Checking this implication will be undecidable in general, but the SORM uses the liquid Haskell refinement type checker, which carefully restricts predicates to a decidable fragment so they can be efficiently decided by an SMT solver. Let's see how all of this applies to the notify followers example. The first statement queries the database, but it doesn't yet access any information in the result, so SORM assigns the set of all users as the authorities. Additionally, since the statement doesn't output data to any user, it infers the empty set as the observers. The second statement is a bit more complicated because it reads sensitive information by projecting the descriptions out of the wishes. By tracking the semantics of the query in the previous statement, the SORM realizes that the code is only accessing the description of public wishes, which should be viewable by the followers of UID. Therefore, it assigns the set of followers of UID as the authorities. Additionally, as the statement doesn't output any data, the set of observers is again the empty set. Now, when sequencing the first two statements, we have to prove the inclusion between the ups and outsets, which in this case holds trivially as false always implies true. Then, by taking the intersection of the authorities and the union of the observers, we obtain the same set of authorities and observers for the composition of the two statements. The following three statements don't access any sensitive information nor output data to any user. Therefore, the authorities and observers sets can be propagated down. The last statement is the first one to output data to a set of observers. And again, by tracking the semantics of queries, the STORM determines that the observers are exactly the followers of UAD. Finally, to prove the absence of leaks, STORM needs to ensure the set of observers in the last statement is contained within the previous set of authorities, which in this case holds trivially as they are both the exact same set. I will finish by presenting an evaluation of our framework. We'll focus the evaluation in three aspects: the expressiveness of STORM policies, the extra effort STORM imposes on programmers, and the effectiveness of STORM at reducing the amount of code programmers need to get right. To test the expressiveness, we ported the models and policy definitions from 10 benchmarks taken from 4 different frameworks, comprising a wide variety of policies. We found that all policies were expressible in STORM, except for one. The sole exception was in Jacqueline's conference manager, and involved the existence of a PC conflicts table and a policy which relied in the absence of rows in that table, which is something we cannot currently express in STORM. It is worth noting, though, that unlike STORM, Jacqueline is a dynamic framework, and that STORM was able to express all the other policies in their benchmarks. Now, even though verification is carried out automatically, STORM imposes some extra burden into programmers. This burden comes in the form of typing annotations, specifying the authorities and observers for some functions. To quantify this effort, we implemented 2 of the benchmarks mentioned earlier in addition to the wishlist application. We show these benchmarks as they represent a wide range of policies. We found out the effort to be quite modest, requiring only 1 line of annotation per 19 lines of code. Finally, to evaluate how effective is STORM at reducing the amount of code programmers need to get right, we implemented 2 full-fledged applications with a polished UI. The first one is Disco, an application that simulates the hallway track to facilitate social interactions in a conference. Here's a quick demo.
Ah, there you are, Nico. I've been waiting to tell you, I just saw this amazing movie, Godzilla v Kong. Have you seen it? It just has amazing effects, and that's kind of a given these days. But even more importantly, it touches on every aspect of the human condition. I think you should just drop whatever you're doing and go and see it right now.
Oh, that sounds amazing. I'm gonna go find the guys and tell them about it. See ya.
Oh, Nico's here.
Oh, hey, Nico. Are you done with your OSDI video?
Yeah, hurry up, dude. This is due tomorrow.
Oh, you're right. I still haven't told them about Voltron. So, see ya. Voltron is an application that allows instructors to simultaneously view the progress of multiple groups of students collaborating on in-class programming exercises. Voltron was used in 4 classes between fall 2020 and spring 2021, ranging between 50 and 200 students. In both applications, the code is divided into a browser-based client written using the Vue.js framework and a STORM server that handles and provides sensitive data. The following table shows the lines of code taken by server, models, policies, and client code. As expected, we can see that policy code is much smaller, taking less than 4% of server code, and if we consider client code, it goes even lower, to less than 2%. In conclusion, we presented STORM, a new web framework based on the model view controller architecture that let programmers specify rich security policies alongside the model and guarantees the absence of leaks automatically and at compile time.